All right, in this video, we will be going over section 2.4. This is about chain rule and implicit differentiation. Okay, this is in particular, this chain rule is one of the most important rules in this whole chapter. Okay, that helps us to do complicated differentiation. All right. First, I want to start with this theorem 2.12, which is the chain rule. Before that, I want to recall a few things from your pre-calculus class, that is composition of functions. Okay. Suppose you have two functions, f and u. What do you mean by composition of these two functions? Well, by definition, here is what we mean by the composition. The composition of f and u, f composition u is denoted by, you write f and you in the middle you put an open circle like this. So that is what we mean by f composition u of x is defined by f of u of x. Okay, for example, let's say your f of x is, here is an example. Okay, f of x is equal to say x cube, and say u of x is equal to x squared plus 1, then how do you calculate f composition u of x? That is by definition, by this definition, this is nothing but f of u of x. Now to calculate f of u of x, you need to plug in u of x inside your function f of x. Okay, this is your u of x. This goes inside this. Okay, you replace your x in the function f of x by x squared plus 1 to find f of ux, because you have to put this u of x as the input of your function f of x. Okay, so then you get this is equal to x squared plus 1 whole thing to the power 3. That is the composition of f and u. F composition u of x is going to be x squared plus 1 to the power 3. You just plug in this u of x in the function f of x to find f of u of x. All right, that's something from your pre-calculus class. Now let's go to the theorem, theorem 2.12, the chain rule. Here is what the theorem tells you. Okay, suppose f of u of x is a composition of functions, then for all values of x at which u is differentiable at x and f is differentiable at u of x, the derivative of f with respect to x is equal to the product of the derivative of f with respect to u and the derivative of u with respect to x. Okay, here is the Leibniz notation for the chain rule. You write df over dx is equal to df over du times du over dx. Okay, logically you can think of this as kind of, you cancel this du and du, then you get df over dx, right, as given in the left hand side. It's just a logical argument, but it's not what is really happening there. And then the other notation is the prime notation. Okay, that's what we are interested in sticking to. Okay, so we will be using this particular notation here onwards. We write the derivative of the composition of f and u in this notation, f composition u prime of x. That means the derivative of f of u of x. Okay, you can also write this way. You put a prime here to indicate that you take the derivative of this inside thing, that is f of u of x. That is nothing but the composition of f and u. So the derivative of the composition is given by, here is what the rule tells you. Here is what the rule tells you. That is f prime of u of x times u prime of x. Okay, again, the derivative of f composition u of x is equal to f prime of u of x times u prime of x. Okay, all right. To understand this rule, let's look at some examples. By the way, for the chain rule, first I will show you how to apply this rule as it is given in this formula, and then I will give you a shortcut to do it more easily. Okay. All right, let's look at these examples. Let's look at, let's read the example first. Find the derivative of each of the following function. Let's work on the first part, part a, how do you take the derivative of this function? By the way, the derivative of this function y is denoted by y prime or dy over dx. Y prime is same thing as dy over dx, okay? How do you find y prime for this function? This is what you want to find, okay? For that, you are going to have to use the chain rule, okay? Because you cannot apply the power rule here directly. Because if you have x to the power 1/2, you can straight away apply the power rule to find dy over dx. That is going to be 1/2 times x to the power minus 1/2. But here we have some complicated expression. It's not x, so you cannot apply the power rule straight away. That's when this chain rule is going to help you, okay? So to apply the chain rule, I need to view this function as a composition of two functions. You need to identify your f of u and your u of x. In order to apply the chain rule, you need to identify your f of u, function f, and then function u, so that the composition of those two functions will give you this function. Here is how I'm going to identify f and u, f and u of f of u and u of x. I'm going to identify my f of u to be u to the power 1/2 and u of x to be x squared plus 1 divided by x. Then notice that if you compute the composition f of ux, you will exactly get this function. To find f of ux, what do? To find f of ux, I plug in my function u of x in my f. You replace this u by this u of x, then you get x squared plus 1 over x whole thing to the power 1/2. So we are good, okay? So we identified our f of u and u of x. Now I'm ready to go with the chain rule. To go with the chain rule, I'm going to need few more data here. That is, I'm going to need f prime of u. F prime of u is 1/2 times u to the power minus 1/2. That is using the power rule. I take the derivative of this function with respect to u. Okay, that is 1/2 times u to the power minus 1/2. And then I take the derivative of this function with respect to x. That is u prime of x is equal to, how do I take the derivative of this function? Now notice that this is a quotient, so I have to apply the quotient rule. So let's apply quotient rule there. I will get some space over here. How do I apply the quotient rule for this function? Well, this is the quotient rule. We have f over g. I will view this as my g of x. This is my f of x. Then g of x squared should be in the bottom. U prime of x is equal to g of x squared should be in the bottom, that is x squared. And then f prime of x, g of x. F prime of x means the derivative of the top function. The derivative of this top function is 2x times g of x. G of x is just x minus, and then you leave the top function fixed, your f of x fixed, and take the derivative of g of x, which is 1, because the derivative of x is 1. Okay, this will give you x squared minus 1 divided by x squared. That is the derivative of u, or u prime of x. Now I'm ready to go with the chain rule formula. What is the chain rule formula? F of u of x, the derivative of this. The derivative of that is denoted by, I write f of u of x and then put a prime here. That means the derivative of f of u of x. That's what you want. Okay. This is equal to f prime of u of x times u prime of x. That will be equal to, I know f prime of u. My f prime of u is 1/2 u to the power minus 1/2. So f prime of u of x, to obtain f prime of u of x, you plug in u of x here and here. Okay, if you plug in u of x in both places, you get f prime of u of x. That is 1/2 times u of x to the power minus 1/2 times, don't forget this u prime of x. U prime of x is this one, this function. That is x squared minus 1 over x squared. Okay. All right. Now let's simplify this further. 1/2 times. Notice that here I have u of x. U of x is nothing but this function. U of x is x squared plus 1 over x. So let me put that in here. X squared plus 1 over x to the power minus 1/2 times x squared minus 1 divided by x squared. Okay, that's your answer. That is the derivative of composition of these two functions. Or in other words, you could write this is nothing but your dy over dx, y prime, because this was your function. This is the function f of u of x. Let me write the last statement. Y prime is equal to 1/2 times x squared plus 1 divided by x to the power minus 1/2 times x squared minus 1 divided by x squared. That is the derivative of this given function. Okay, that's how you apply the chain rule. First, you need to summarize, first you need to identify your f of u and u of x such that f of u of x will give you the function that you want to differentiate. Okay, I identified my f of u and u of x, and then I find f prime of u, that is 1/2 times u to the power minus 1/2, and then I find the derivative of this function u prime of x. That is, of course, I can copy this over here. That is going to be x squared minus 1 over x squared. Okay, and then I can go with the chain rule. Okay, so this is my function. This is the function I am interested in. F of u of x is this function. That is the given function. So I need to take the derivative of that function. This prime notation means the derivative of this function, or in other words, y prime. That is equal to, by chain rule, f prime of u of x times u prime of x. To find f prime of u of x, I plug in u of x here. That will give you this. And then to find u prime of x, of course, I found the u prime of x earlier here. Okay, you plug in that here to get u prime of x. And then I can do one last thing. I can replace this u of x by this expression. Okay, to get the final answer. This is my y prime. Y prime is equal to this. Okay. All right, that's how you apply the chain rule. Now I want to show you a shortcut for the chain rule. Okay, so here is how the shortcut works. I would call this shortcut the star rule. Okay, what does the star rule tell you? Okay, suppose you have a function of this form, y is equal to star to the power k. How do you differentiate this one? This, by the way, this star means you have some complicated expression. Okay, star means it's a complicated expression. It's not x. How do you differentiate this function? Or in other words, how do you find y prime for this function? Well, let's go back and think about the simple power rule. If you have x to the power k, you know how to handle this one, right? If you have x to the power k, you know how to handle this one. The derivative of this one would be y prime is k times x to the power k minus 1, right? That's something that we learned in the previous sections. Okay, now the problem is here, we don't have x now. We have some complicated expression, which I call the star. Okay, now how do you handle this? Well, you handle this case also the same way that you handle this case. You had k times x to the power k minus 1, right? I do the same thing here. K times my star to the power k minus 1, but I'm not done here. I'm not done here because I did not have x here. I had a complicated expression here. So I have to pay a penalty. The penalty that I have to pay is you need to multiply this expression by the derivative of this star. Multiply this expression by the derivative of the star. The derivative of the star is denoted by star prime. then I'm done. Okay, that's how you modify this rule to get the derivative of this particular function star to the power k. What do you do again? You apply this rule that you applied for the basic function x to the power k as it is here. That is k times your star to the power k minus 1. You are not done yet because you had a star here. So you have to pay a penalty. The penalty is that you multiply that expression by star prime. Star prime means the derivative of the star. Okay. All right. Now let's go back and do the same problem that we did earlier using the chain rule, using this shortcut, okay, which I call the star rule. So my y prime is equal to, notice that in this case, my star is this function, x squared plus 1 over x. So to apply the star rule, I should have 1/2 times my star to the power 1/2 minus 1. 1/2 minus 1 means minus 1/2. I just apply this rule. Okay, k times star to the power k minus 1. That is 1/2 times star to the power 1/2 minus 1, which is minus 1/2. Now you need to multiply this thing by the derivative of my star. My star is this expression. So the derivative of that x, you need to multiply this by the derivative of your star. That is denoted by star prime. Okay, this expression prime means the derivative of this expression. Okay, you are not done yet. You need to find the derivative of this expression. Okay, let's do it. This is equal to 1/2 x squared plus 1 divided by x to the power minus 1/2 times, you need to find the derivative of this expression. How do you find the derivative? You found the derivative in the previous method. Okay, so you found the derivative of this expression. The derivative of this expression was this one. You applied the quotient rule, x squared minus 1 divided by x squared. So let me put that here. X squared minus 1 divided by x squared. Done. As you can see, you get the same answer using both methods, using the shortcut and using the actual chain rule. See, these answers are same. Okay. All right. To get used to this shortcut, let's do another example. Actually, we do two examples. Let's work on part B. I think it is part B. Yes. This is part B. How do you apply your star rule for this example? Again, notice that your star in this case is this expression and your k is this one. Okay. To find the derivative of this one, we apply the star rule. So we should have minus 2 times your star minus 1 over x to the power minus 2 minus 1. See, if you have star to the power k, that should be k times star to the power k minus 1 times the derivative of the star. So I got minus 2 times, this minus 2 comes to the front, to the power, minus 2 times star to the power k minus 1 times the derivative of my star. The derivative of my star is square root of x minus 1 over x, the derivative of that. I need to calculate the derivative of that. That's a different story, but this is the y prime. This whole thing is y prime. Now let's go ahead and calculate the derivative of this one to finish the problem, to complete the problem. Okay, so this is going to be equal to, first of all, to calculate the derivative here, notice that square root of x minus 1 over x means nothing but x to the power 1/2 minus x to the power minus 1. Because the square root of x is x to the power 1/2 and 1 over x is nothing but x to the power minus 1. Okay. Now, if you take the derivative of this one, square root of x minus 1 over x, the derivative of that is equal to 1/2 times x to the power minus 1/2 minus, you apply the power rule here, then that becomes plus, this becomes plus x to the power minus 2. This is the derivative. This thing is the derivative. That means I can replace this whole thing by this derivative. Okay, so This is equal to minus 2 times square root of x minus 1 over x to the power minus 3 times 1/2 times x to the power minus 1/2 minus plus, pardon me, x squared. I just replace this by the derivative of this function. The derivative of that function is 1/2 x to the power minus 1/2 plus x to the power minus 2. Okay, so that is the derivative here. The derivative of this function, I put it here. Okay, this is the answer. Done. Okay, let's work on the other last part using this star rule. I'll copy this one to a new page. Okay, so how do you find the derivative of this function? Y is equal to x squared plus 1 cube minus 2x minus 1 squared. First of all, you need to apply the product rule. Okay, let me copy the product rule. Yeah, product rule is over here. Okay, so we need to find the derivative of this function. That means you need to find y prime. Okay, to find y prime, I'm going to view this as my f of x. This is my f of x. This is my g of x. It's a product. So I can apply this product rule. Here is how you find the derivative of a product. Okay, so my y prime is equal to f prime of x. That means the derivative of the first function. Now the question is, how do you take the derivative of this function? Here you have to use the star rule. Let me recall the star rule again. You have y is equal to star to the power k. The derivative is equal to k times star to the power k minus 1 times the derivative of the star. Okay, you apply the basic rule first. K times star to the power k minus 1 times the derivative of this star. The derivative of this star is star prime. Okay, that's what I'm going to do here. See, this looks like a star because I need to have f prime of x here first. That means the derivative of this one. To get the derivative of that one, I'm going to use this star rule. Okay, now your star looks like this one, this function. Okay, so that will be 3 times your star to the power 2 times the derivative of the star. The derivative of your star is 2x. 2x. Don't forget this function. G of x should stay there as it is. Look at this formula. G of x. That is 2x minus 1 squared. And then plus, I need to complete this part. F of x times, of course, my f of x is this whole thing. This whole thing. That is x squared plus 1 to the power 3 times the derivative of g prime of x. That means you need to take the derivative of this function. Again, you are going to use the star rule. Here is your star. You have star to the power 2. So the derivative of that would be 2 times your star, 2x minus 1 to the power 1 times the derivative of your star. The derivative of your star is 2. That means the derivative of this function, which is 2. You need to have 2 here. Okay. All right. This is the final answer. Of course, you can simplify this a little bit further if you want, but you can leave this as your final answer. All right, let's move on. The next thing I want to talk about is implicit function. When do we say that y is an implicit function of x? Well, we say that y is an implicit function of x if we cannot solve an equation for y and obtain a single well-defined function for y. Okay. For example, if you take an equation like this, in this equation, you cannot solve this equation for y and obtain a single well-defined function. Or in other words, in this equation, for a given x value, you may have more than one y value. That means y is not a function of x. Okay, you cannot solve for y and obtain a single well-defined function. And in fact, if you graph this one, you know from the pre-calculus class, the graph of this function, not the function, this relationship would give you a graph like this. It's the unit circle, right? This radius is 1, center is at the origin. This is the equation of this circle. As you can see, it is not a graph of a function. By the vertical line test, if you draw a vertical line, that vertical line is going to intersect your graph at 2 points. That means it's not a, y is not a function of x. Okay, but it is a relationship. Okay, this kind of a situation where you cannot solve this equation for y and obtain a single well-defined function in terms of x, we say that y is implicitly defined as a function of x. Or in other words, y is an implicit function of x. Okay, and of course, even though we cannot solve for y and obtain a single well-defined function, you can obtain two functions here. Okay, so if I try to isolate my y, you get y squared is equal to 1 minus x squared. I'm just moving this x squared to the other side. Then to find my y, I take the square root of both sides. Then you get plus or minus square root of 1 minus x squared. So that means you get two functions. First function is square root of 1 minus x squared. The second function is minus square root of 1 minus x squared. Now we have two functions. We didn't get a single well-defined function, but we get two functions. Okay. Now, if you try to graph these two functions, you will immediately see that the first function will give you the top half of the circle, and the bottom function will give you, or in other words, this function will give you the bottom half of the circle. Okay, that will complete the circle. Okay, in that case, in a case like this, we say that y is an implicit function of x. Okay, that is because we cannot solve for y and obtain a well-defined single function. Okay. All right. Now, the next thing I want to talk about is implicit differentiation. Okay. So we need to find a way to differentiate equations like this. Okay. How do you differentiate? How do you find dy over dx for this type of equations? Why is it important to find dy over dx for an equation like this? What is the importance of finding the dy over dx for an equation like this? Well, suppose on the circle, you have a point. At this point, you need to find the slope of the tangent at that point. Okay, we know that the slope is dy over dx. That is the derivative of your function, right? So if you know a formula for dy over dx, I can plug in this point into my dy over dx to find the slope of this tangent line. Okay, that's the one use of finding dy over dx in implicit functions. Okay, when y is given as an implicit function of x. All right, let's look at some examples to understand what's going on here. Here is the examples that I want to look at. Each of the equations that follow defines y as an implicit function of x. Use implicit differentiation to find y prime. Okay, so how do you find y prime? Let's focus on the first part. How do you find y prime for this first part? Y prime is dy over dx. Okay, recall that y prime is dy over dx, or the slope. Dy over dx is the slope. Okay, slope of the function y. Well, what you do is you differentiate both sides of this equation with respect to x. Okay, so let's do it. Let's differentiate the first term. The derivative of the first term with respect to x is 2 times 2x to the power 1. That is 2x. You take the derivative of this one with respect to x. So this constant stays as it is, and the derivative of x squared is 2x. And then you need to take the derivative of 3 times y to the power 3 with respect to x. Here you are going to have to apply the star rule, because here, see, this is not x. You cannot just write 3 times 3y squared. You cannot just write that, because now you need to view this as your star. Okay, if this is star, what is the star rule? We have y is equal to star to the power k. The derivative of that function would be k times star to the power k minus 1 times the derivative of that star. You need to apply that rule here. Why do you have to apply that rule? Because you don't have x here. You have something else here. It's a different one. So you need to view this as your star. So I'm going to apply the star rule. 3 times y to, pardon me, 3 times, again you have a 3, y to the power 2 times the derivative of the star. Derivative of the star means the derivative of y with respect to x, which is y prime. Derivative of y with respect to x is y prime. All right, again, what I did was I left this 3 as it is and then took the derivative of this y cube using the star rule. That is 3y squared times the derivative of your star, that is y prime. And then I take the derivative of the next term, which is clearly 1, plus finally I have to take the derivative of this one, that is y prime, plus y prime. What is the derivative of my right hand side with respect to x? That is 0 again, because it's a constant. 0, the derivative of 0 is 0. Now remember, my goal is to find y prime. Now what I'm going to do is I'm going to pull out y prime from these two terms. Okay, if I pull out y prime, you get 9y squared plus 1 times y prime. And then at the same time, I'm moving these two terms to the other side. Then you get minus 1 minus 4x. So your y prime is equal to minus 1 minus 4x divided by 9y squared plus 1. You divide both sides by this expression. Okay. Okay, this expression gives you y prime. Y prime is nothing but dy over dx. Okay. Okay, let's look at the next example. Okay. Let me copy this to the other side. Okay, if I copy this. Okay, so now how do you find y prime for this implicit function? Okay, y is given as an implicit function of x. How do you find dy over dx for this one? Again, we use the same technique. We differentiate both sides with respect to x. Let's differentiate this first term. Then you have to apply the product rule there, right? You first take the derivative of, let me actually write, differentiating both sides with respect to x. Then you take the derivative of x cubed, which is 3x squared, and leave y fixed. And then plus, now you leave your x cubed fixed and take the derivative of y. The derivative of y is y prime. I'm done with the first expression. Now I take the derivative of this one, the second expression. That is going to be, you take the derivative of x, which is 1, and leave y cubed fixed. And then plus, you leave your x fixed. You leave this function fixed and take the derivative of the second function. Now, when you take the derivative of the second function, notice that you have to apply the star rule. You cannot just write 3y squared because this is not x, this is y. In that case, you have 3 times y to the power 2 times the derivative of the star. Your star is y in this case. Derivative of y with respect to x is y prime. This is equal to, what is the derivative of 1 with respect to x, which is 0. Derivative of a constant is 0. Now again, I'm going to do the same trick. I'm going to pull out y prime. If I pull out y prime, you get y prime times x cubed plus 3xy squared. And at the same time, I'm going to send these two terms to the other side. Okay, so then you get minus 3x squared y minus y cube. Now to find y prime, I'm going to divide both sides by this expression. Minus y cubed divided by x cubed plus 3xy squared. Okay, this is y prime, or dy over dx. All right, let's move on. And next, I want to work on another example. Consider the equation. Again, this y is given as an implicit function of x. Show that y cubed minus 5x plus 2 factors as y minus 2 times y squared plus 2y minus 1. It is not difficult at all. All what you do is you need to show that these are the factors of this one. What you do is you simplify this and show that you obtain this. Y minus 2 times y squared plus 2y minus 1. Okay, I'm going to use FOIL. You multiply this by this, this by this, this by this, and then you multiply this by this, this by this, this by this. That's the usual foiling. Okay, you foil this one. You get y cubed plus 2y squared minus y minus 2y squared minus 4y plus 3. Notice that 2y squared minus 2y squared, they are cancelled. And here I can combine these two like terms, which is minus 5y. This is equal to y cubed minus 5y plus, yeah, actually this should be plus 2, right? That's not 3, plus 2. That's what exactly we have here. That is the same thing as here. So that means this is equal to this. So the factorization of this one is nothing but y minus 2 times y squared plus 2y minus 1. Okay. Okay, now let's go to part B. If x is minus 5, find all possible values for y. Okay. So what you do is you plug in x is equal to minus 5 in the equation given to you. If you plug in x is equal to minus 5 in this equation, you get, put x is equal to minus 5. Then you get y cubed minus 5y plus 2 is equal to 0. That's what you get. Remember, you need to find all the y values such that x is minus 5. That means you need to solve this equation. Okay, you need to find all the y values that satisfy this equation. How do you find y values that satisfy this equation? Well, you need to find the solutions of this equation. Okay, for that, I'm going to use the factorization that I found in the previous step. I know that this is the factorization of this expression. That means I can write this can be factored this way. Okay, so let me do that. That is y minus 2 times y squared plus 2y minus 1 is equal to 0. I just replace this by this factorization. Okay, so now I can easily solve this equation. From this equation, you get y is equal to y minus 2 is equal to 0, or y squared plus 2y minus 1 is equal to 0. That's because this is a product. See, this expression times this expression is 0. That means y minus 0, y minus 2 has to be 0, or the other expression has to be 0. From this one, you get y is equal to 2. And to solve the other one, you use the quadratic formula. Okay, the quadratic formula, I'll recall the quadratic formula. If you have a quadratic equation x squared plus bx plus c is equal to 0, the quadratic formula is given by this equation. This is x is equal to minus b plus or minus b squared minus 4ac, the square root of that, divided by 2a. Okay, using this quadratic formula, this is the formula coming from your pre-calculus class. Okay, using that formula, you can find the solution of. Okay, if you solve for y, these are the values you obtain using the quadratic formula. Okay, minus 1 plus the square root of 2 and minus 1 minus the square root of 2. Okay, if you want to write them as points on the curve of the given relationship, the points would be minus 5, minus 5, comma 2, one possible point. The other point is minus 5, comma minus 1 plus the square root of 2, and then minus 5, comma minus 1 minus the square root of 2. All these 3 points are on the given curve. Okay, the given curve is this one. Notice that your x value is minus 5 in all these 3 points because you set your x value to be minus 5. All right, let's go to the last part. Find the slope of the tangent to this given curve at the point minus 5, comma 2. Minus 5, comma 2 is the first point that you found. Okay, so you need to find the equation of the slope of the tangent to this curve at this point minus 5, comma 2. To find the slope of the tangent, you need dy over dx, right? Slope means dy over dx. So let's try to find the dy over dx for this equation. How do you find dy over dx? Well, I'm copying my equation here. Let's use the implicit differentiation to find dy over dx. I'm going to differentiate both sides of this equation with respect to x. If you differentiate the first expression, that is y cube, you get 3y squared times y prime. Remember, I'm going to have to apply the star rule here because this is your star now. It is not x. Whenever it is not x, that is going to be a star. Star to the power 3 is 3y squared times the derivative of the star, that is y prime. And to get the derivative here, I'm going to apply the product rule. So the derivative of x, which is 1 times y, plus you leave x fixed and take the derivative of y, which is y prime, plus the derivative of 2 is 0, is equal to the derivative of the right hand side is 0 again. Now I can pull out a y prime from these two terms and I can send this term to the other side. I'm sending this to the other side. Then you get 3y squared plus x times y prime is equal to minus y. That will give you y prime is equal to minus y divided by 3y squared plus x. That is your dy over dx. Remember, but in the problem, you are asked to find the dy over dx at a particular point. At this particular point, you are asked to find the dy over dx or the slope of the tangent to this curve at this particular point. Okay, so that means you need to plug in this point. You can plug in that point. So that means the x value is minus 5, your y value is 2. Okay, so if you plug in x is equal to minus 5 and y is equal to 2, that will give you the slope of the tangent at that point, minus 5, 2. So that usually we denote it by, this is dy over dx, okay? Y prime is always dy over dx. Dy over dx when x is minus 5 and y is 2 is equal to minus 2 divided by 3 times 2 squared plus minus 5. If you simplify this, you will get minus 2 over 7. Okay, that's the slope. All right, now what if you are asked to find, in addition to the slope, what if you are asked to find the equation of the tangent to this curve at this point? Well, you can use the point slope form of the equation of the line to find the equation of the tangent. If you are asked to find the equation of the tangent, okay, y minus y1 is equal to m times x minus x1. Of course, your value of m is minus 2 over 7. That will come here. And your x1, y1 is nothing but minus 5, 2. Okay, I'm not going to do it. All right, the next thing I want to talk about is another application of the implicit differentiation. Remember, in the previous section, I told you that we can differentiate. We can prove the power rule when your power is a rational number using implicit differentiation. Okay, that's what I'm going to show now. Okay, using implicit differentiation, we can show that the power rule holds even when you have a rational power. Okay, so we want to show that. First of all, let's read the example. Find the derivative of y is equal to x to the power p over q using implicit differentiation. Here, p over q is a rational number. Of course, in the previous section, we proved this formula for the case, the power rule for the case when k is a positive integer. When k is a positive integer, y prime is equal to k times x to the power k minus 1, right? We proved that. Also, we left the case when k is a negative integer as an exercise for you in one of the homework assignments. When k is a negative integer, y is equal to x to the power k, then also y prime is equal to k times x to the power k minus 1. So that means when k is a positive integer or a negative integer, this formula holds. Okay, the derivative of that would be k times x to the power k minus 1. Now I want to show a similar thing hold here when the power is of the form p over q. It's a rational number. Okay, so this is what I want to prove. Need to show y prime is equal to p over q times x to the power p over q minus 1. Okay, if you think of this whole thing as k comes to the front, x to the power k minus 1. A similar formula should hold even when you have a rational power. That's what we are going to prove here. Okay, so let's see if we can prove this formula for this given function using implicit differentiation. Here is what I'm going to do. I will copy this to the other side. You have y is equal to x to the power p over q. Now I'm going to raise both sides to the power q. Then you get y to the power q is equal to x to the power p. Now I'm using implicit differentiation. Okay, so now I'm going to differentiate both sides of this equation with respect to x. Then you get, notice that when you differentiate both sides of this equation with respect to x, this looks like a star. Okay, so you have to apply the star rule there. That is q times y to the power q minus 1 times the derivative of the star y prime equals, now here you have no problem because you have just x. So you can apply the power rule straight away. P times x to the power p minus 1. Now I'm going to isolate my y prime. That's what I want. Y prime is equal to p over q times x to the power p minus 1 divided by x to the power y to the power q minus 1. But I know my y is this one, x to the power p over q. So I can put that y here. If I do that, you get p over q times x to the power p minus 1 divided by x to the power p over q to the power q minus 1. Okay. Now using the exponent rules, we can simplify this further. You get x to the power p minus 1 divided by x to the power p minus p over q. All what I did was I multiplied this by this power to get this. Okay. Now I further simplify this. Notice that you have the same base in the top and bottom. So I can subtract powers, this minus this. Okay. So this will become P over Q times x to the power P minus 1 minus P minus P over Q. Now, if you simplify this expression, P and P cancel, right? Plus P minus P, they are cancelled. You get P over Q times x to the power P over Q minus 1. This is minus 1. Minus times minus plus, you get plus P over Q. So it is P over Q minus 1. This is what exactly we wanted to prove. We wanted to prove that y prime, the derivative of this one is P over Q times x to the power P over Q minus 1. Okay, this completes the proof. So this power rule is true even when we have a rational power of the form P over Q. Okay. By the way, this power rule for the case when k is a negative integer is left as an exercise, as I mentioned. Okay, we proved this case when k is a positive integer. All right, with that, we conclude section 2.4. I will stop there and I will see you next time.